Hello everyone, welcome to another YouTube tutorial on using STK and other associated software I work with. Today I want to talk about putting together or aligning two STK molecules, something that I've always, needed to do, and it's often a common problem, but it's quite difficult to do for large complex molecules like cages. So I'm showing this video because we recently pushed a new optimizer to stko called the Aligner, and it uses spin-dry code I've shown previously for generating host-guest conformations to align two molecules. I'm going to start by showing the actual source code for the Aligner. And I will just zoom in. The main thing I want to show and what this is based on is a new feature of spin-dry, which is the ability to use a custom potential or implement a custom potential. And here, for this problem, I've implemented the alignment potential. And all this does is take the define the potential based on a parabolic cost for how far two atoms are apart from each other. And the two atoms of interest are the nearest pair of two set element types. So if you set the element types to be carbon and carbon, it'll be for each carbon atom in one molecule, the potential will be relative to the distance of the nearest carbon in the other molecule. So it's not set which atoms are used in this pair function. And it's determined based on the conformation of the two molecules. And I found this potential to be quite useful for running the aligner and aligning two molecules. The only other thing I'll show in the source code before I get started is the way it works is to run spin-dry multiple times, I think 30 or 40 times, with different initial configurations. So these rotation axes and angle terms take your initial molecule, take your molecule to be aligned to, and it rotates them about some rotation axis by some angle, and this is just kind of covering a sphere basically. And so these initial configurations are all tested based on spin-dry, and then that is and then the kind of the best matching pair is what's output by stko. So I just want to show three examples of it being used with STK molecules, and I've kind of already run it because it takes a bit of time to write and run to run the code, and I just want to run through step by step kind of what happens. So we start by importing stk and also the time module to time these things. We have a simple molecule, caffeine, so if we get up pi mole, you can see the initial molecule, the unaligned molecule, and then we can set the matched pairs. So these are the element types to use in the alignment potential. You could put all of the atom types, so carbon, nitrogen, oxygen, and hydrogen, or whatever's present in your molecules, but this actually produces quite a noisy potential surface. Basically, I'm using that in quotations because it's not a physical thing, I guess, and that's not right. And so what we actually use are heteroatoms normally. So for caffeine, I use nitrogen and oxygen. We define the optimizer in standard stko fashion. We have some initial arguments. So the initial molecule is the target molecule. The matching pairs set define the pairs used in the alignment potential. And then, as per all STK optimizers, we run the optimizer class.optimize on the unoptimized molecule or the unaligned molecule. And we get out an optimized or aligned molecule. We can then write that to align.mol, and you can see for 24 atom molecule like caffeine, this takes about 4.5 seconds. So it's not that efficient. But when we visualize this, we see it does quite a good job. They're aligned, they're not perfectly aligned, right? They're the exact same molecule, so they're not perfectly aligned, otherwise they would be completely overlapping. However, I think you would have to run much longer spin dry simulations to get that to happen. Cool, so we, as part of this, introduced an Rmsd calculator as well, to quantify how well aligned two molecules are. And you can see that the unaligned molecule obviously has a high Rmsd, the aligned one has a low one. Again, not perfect, but yeah, not perfect overlap for the same molecule, but it does a decent job. I would not recommend this for small molecules because there are better algorithms out there, such as Arbor-Line, I think. However, for not so simple molecules, when we're looking at a palladium metal organic cage, so I'll show these in PyMol now, but these are 186 atoms, and we can see the initial cage structure and the unaligned one. And so aligning these in ArbMol, from my experience, is difficult, but I might have missed how to do it properly. And this also is much more difficult when you have molecules generated by different software, for example, and the atom IDs don't match. None of that matters to this aligner optimizer. So you can throw in two different molecules and get out alignment between them. So in this situation, we can use either just the nitrogens or the nitrogens and the palladium atoms to do the potential function. And we run the exact same. The interface is the exact same. We can calculate the Rmsd, and showing here the time taken now for about 200 atom systems is about 200 seconds, or 3 minutes for both. This one's more like 4 minutes. And the Rmsd is quite good. It's better in the case of just using the nitrogens. But if we visualize the structures, you can see what's happening in both instances. You have just this shift of the molecule kind of systematically, which is causing the mismatch. So that's with just the nitrogens, and then if we look at the nitrogens and the palladiums in the system. And I expect this is due to the setting of the potential function, so you can change the width or something. I intend on updating the interface of stko to allow more controllability over the potential function that's used. Cool. The final example I want to show is a bit more complicated, but may be useful for visualization. I think is where this comes in handy. And so we have two host-guest systems. They are the same guest, but they are distinct. So same guest but distinct hosts. So if I can just grid mode these. They're the same guest but distinct hosts, and we can see that. And there's kind of two things you might want to do. You might want to align the guests, or you might want to align the hosts. And I show, based on the match pairs, that you can actually do this if they happen to have distinct atom types. And so we have the first example where we align the hosts. And this takes again about 260 seconds, so like about 4 minutes. And the first thing I need to point out, I need to take a quick detour. This actually, they're two distinct stk molecules, right? And that aligner has no problem. It runs it, but it throws out an error in the Rmsd calculator, and it throws out a different molecule exception because they're not equivalent molecules. That's because the default Rmsd calculator assumes the same atoms, they assume exact equivalence of the molecules, so the same atoms, same atom IDs, and same atom ordering. That is not ideal in all cases. So I also wrote the Rmsd mapped calculator, where, similar to the alignment potential function, it calculates the Rmsd of one atom based on the nearest atom of the same element type. So it's not exactly clear when you're running it which atom is being used in the RMSD, but it'll always be the nearest of the same element type. And this means you can calculate an RMSD of distinct molecules or molecules with different atom ID orderings and so forth. However, it also does mean that if you have very unaligned molecules, this number is probably meaningless. But once they're aligned and the atoms are actually close, it should have some meaning. And when we run this now, we get no error, fortunately, and an RMSD out. By changing the match pairs to be oxygens and bromines, we can align the guess and again calculate an RMSD between the whole molecule. And when we visualize this, so we've aligned it all to this molecule. We have the host aligned system. You can see that, they're aligned, they're not perfect, but they are aligned. And then the guest aligned system, which again, it's not perfect, but you can see that the bromines and the oxygens are kind of pointing in the same way, which is, I guess, a good start. What you'll notice comparing the host and guest aligned system is that it flips the molecule, right? And this is where those initial configurations are important for looking at these large changes, because spin drive will orient and shift the molecules in small amounts, while those large initial configuration changes give you these large shifts. Anyway, that's the end of the video. That's all I wanted to show. All of this is available on SDK examples, and my GitHub repos, and a blog post will be coming as well. Thank you very much.